So we're going to kind of pick up where we left off discussing multiple linear regression examples or topics. So we should be able to complete everything today. So I'm thinking on Thursday's class, I'll probably review some of the more of the stuff we go over today, a little bit more in Stata and what we have time for today. And then we'll probably even kind of start picking up on review. So that practice of exam, along with the formula sheet that you'll have for the exam, just to kind of give out some, start thinking about the exam coming up, not this Thursday, but next Thursday, right? Is if I was kind of preparing for this, the first thing I would sit down and do is I would look at this formula sheet, which will be given on the exam, and I would identify what every single one of these equations means. Okay, so it's all notation based. This is all you'll have. You can't use like your own one that you create, but in creating it, right, and as you're studying with it, there's a little bit of kind of, memorization, like you can kind of remember my formula sheet I was studying with. I'm going to give you the exact same order of formulas so you can remember, oh yeah, that first one was the variance of just a random variable that had probabilities associated with seeing different values. Or, oh yeah, this was my test statistical equation, right? So I would kind of go through, write down next to each one of these formulas what they represent, maybe even kind of indicate what everything in that formula represents. It's kind of a good way to remember like the statistics that we're looking at, and kind of how we could calculate them given different output or given different state output. After that, I would then go and start to look through these practice exam problems. So when I give practice exams, this is something that maybe I'm speaking over, underneath you guys, but I notice this a lot, but I teach a lot of freshmen, is it's meant to be not so much a practice exam and that like sit down, take it and see what your score is. Because if I simply take an exam twice, it's different questions, I'm probably going to get a pretty similar score, right? I mean, I haven't really learned a whole lot from just taking the exam. So what I would do is I would kind of go through this. If you want to use it as a practice exam, you kind of get an idea about where you're at, your understanding's at, that's fine. But I would work through every single one of these problems and I would try to look at the answer key, right? Maybe I want to work through it on my own first. Okay, did I get it right or wrong? Even if I get it right, why is the correct answer what it is? I should be able to provide some proof to myself, right? Using some type of equations, right? And mostly in this class, it's going to be a lot of equations of why that correct answer is what it is. Okay, so working through this practice exam and solving each question, having actual proof as opposed to like, okay, I think the test statistic is this. So if the standard error goes up, I think it's going to make it more or less statistically significant. So I think that's the answer. Actually be able to provide support as to why the correct answer is what it is. That's how I would work through these practice exam problems to kind of help improve my learning. Now, I gave you these problems because they're probably going to look pretty similar to what you see on the exam. Now, you'll notice some of them are multiple choice, some of them are open-ended. I might have looked at this a little bit when I showed you this the first time. So what the exam is going to look like, I'm still kind of debating, and I might have a kind of poll in class on Thursday. So if you're in class Thursday, your preference will be kind of weighted more than someone who's not because they won't be responding, right? But I'm imagining that what I'd like to do with this exam, and once again, I always try to get a little bit of feedback to kind of see what your preferences are. But I could give you this exam with multiple choice and fill in the blank, kind of similar to this practice exam, have you take it an hour and 15 minutes. It's not a lot of time. It's going to feel a lot more stressful. And so what I'm tentatively thinking of doing is giving you an in-class portion of the exam, in which case it's primarily open-ended. I'm then going to give you kind of a multiple choice portion of the exam that you can take anytime after Thursday's class until the following Tuesday. It gives you a little bit more time, and I work it into your schedule. Now, if I do that, right, I have ways on Canvas of making sure you're not all seeing identical questions, right? And really what that mainly becomes is like just changing values, right? Or changing increase to decrease, showing you kind of a batch of questions, you're seeing slightly different values than someone else. So I can kind of ensure that there's not kind of some cheating going on, right? So the multiple choice questions might become a little bit more difficult in that sense, but it gives you a lot more time to answer them, and it gives you more time to answer those kind of open-ended fill in the blank questions in class.
Will that one also have a timer?
On the, yeah. So you can't just like pick up and stop, right? But you'll have kind of more time per question if you want to think about it that way. Now, you're sitting down, you'll kind of have like 60 minutes to answer those multiple choice questions, whatever the exact time I decided is. I haven't kind of worked that out entirely. I'm still kind of working on fine tuning that midterm. If I've got questions, I'm trying to get the point total to be what I want and kind of taking some questions out or on. So I'll probably have it finalized by the time we meet in class on Thursday. That's my goal tomorrow. But that's tentatively what I'm thinking this exam is going to look like. Okay. So you will see multiple choice type questions, but you're also going to see plenty of kind of open-ended, right? So each question I would think about, how could I maybe turn this into a multiple choice, or how could a multiple choice kind of, if I had to answer this open-ended, how could I maybe kind of see this question change a little bit? And it, really should primarily be like, at the end of the day, what have we done? We've done review of basic statistics and kind of hypothesis testing. We've done simple linear regression, and now we've looked at multiple linear regression. So that's kind of our topics that we're looking at, okay? So I would also, going back to the old quizzes, going back to old practice problems, those are also good things to kind of review. Once again, if you got the quiz question right, make sure you can answer why the answer was correct, right? Even if you got it correct, can I provide some proof that if I had things change in this problem, or they asked me for a slightly different statistic or something like that, could I answer that question? Okay. And like I said, we'll really be getting a lot of review in Thursday and Tuesday as well. So I'll kind of point some of these things out along the way, but just kind of thinking as we're getting closer to that exam. Okay. Other than that, we've currently got that quiz, which I think I've got here set to be the end of the day on Thursday. Right. So you still, if you haven't taken that third quiz, you still need to take that. You've got the practice problems for that. We've covered all the material. So anything like we do today won't show up on that quiz. Right. And then you have, where is it? That third problem set, which I don't have set to be due until the end of the day next Tuesday. Right. So you've got a little more time to kind of work on that problem set. So I'm pretty far through grading the second problem set. I'm hoping that grades will either be finished tomorrow. Part of this, I think I mentioned with the first one, I'm kind of help teaching my graduate assistant how to grade assignments like this. And so I'm relying on them a little bit as well. So it might spill over a little bit into kind of towards the end of the week. But you should have those all graded, and I'll get actually a solutions file posted by the end of this week. Okay. So that would be another good thing to review, is that kind of second problem set. Now, obviously, you won't have as much time with the third, but after Tuesday's class, or after Tuesday ends, I'll get up a kind of solutions file of problem set 3 if you want to look at that on Wednesday, kind of leading into the exam as well. Okay. Now, one thing I'll kind of mention about these problem sets I'm noticing as I'm grading, I know a lot of you aren't doing the work, which I guess you're cheating yourself, so it's on you. I mean, I'm flagging some, in which case some of you might be hearing from me, but I'm seeing almost nearly identical do files turned in. It's pretty easy to identify when you're making certain mistakes similar to someone else that are pretty rare. Also, you're using things in your code that we have never talked about. Now, some of you might just be very motivated. You go out and you try to kind of learn more of Stata on your own. Maybe I'm pessimistic. I don't believe that's probably the vast majority. Okay. So you can get through these by looking at, I'm guessing, old solution files. What do you think I probably do semester to semester? Can I use the exact same homework? So I change things. So when you start to use dependent variables that I didn't mention in the problem, what do I think you're probably doing? I think you're coming up with it on your own, and you just happen to accidentally pick the wrong variable. I mean, I'm not dumb. You guys don't, you can tell me the honest truth. I'm not going to penalize, but like, you're probably looking at an old file and you're just using old problems, which is not the questions that I asked. Or I might change the question slightly, so your answer makes absolutely no sense compared to what was actually asked in the question. So you're losing a lot of points. So there's going to be some of you who see your grade for that second problem set, and you're going to be like, well, I copied this old thing. I looked at the old one. You got to read the questions I'm giving you, right? If you're not answering those, you're not going to get the full point. Also, if I'm asking you for reasons why, be complete in your answers, right? If you're just kind of looking at an old one where maybe I didn't ask why, maybe they got full points on that because that wasn't part of the question, and you're going to lose points because you didn't follow up and answer everything in that problem, right? So the point of these problem sets is not for me so much, I really think the value in this class, and I don't like grading, these take a lot of time to grade and write. the value is like, if you have this skill to be able to work with data in a data management program, you just became way more attractive on the job market than a lot of other econ majors, right? In fact, you can compete with these Kelly kids. Right? I tell plenty of my Kelly students all the time, like, if you want to take 371, I know some of the stats stuff they're doing, and Kelly isn't even near kind of what we get to do in this class in terms of the actual programming side of it, right? So, once again, you're probably cheating yourself. Now, if you get these mistakes wrong, you're also going to lose points, right? Answering the actual questions. But try to take these a little more serious, right? And when I start to see things that look suspicious, right? If I have enough evidence to support that you're using old files, you might be getting an email from me. Okay? If I know you're just handing in something from another semester. Now, didn't have anybody that brazen, at least the ones I graded up to this point, and turning the complete old file. And those old ones are probably be useful and kind of helping you, right? Make sure you're reading the actual assignment, okay? So that's my kind of 2 cents in my spiel before we get going here. So any questions for me related to the class before we jump into new material? Yeah.
When we're doing problem set 3, we use the different DTA file. Do you want us to mention that we're using the other DTA file?
Well, I assume you are if you're going to answer the questions that need those variables, right?
Yeah.
So, I mean, if you open it up and you don't have the code to open it, I'm not going to grade you on that. Although at some point you really should be running the code to open the first file and then later on opening a new file, right? If you don't save that in your do file, it's not part of any question to grade you on, but you'd have to open up the second data file in order to answer the questions that are related to that second data set.
Gotcha.
Does that make sense? Yeah. Okay. Also, some of these problem sets, I mentioned some of this work is done in Stata and some of this work is done by hand. Now you can use the comments. Some of you upload PDFs to kind of show your work, in Word or whatever it is. But there was a problem on here where I gave you output. There's nothing you had to do in Stata, and I left out some blanks, right? And then knowing what we know about the statistics, you had to use that Stata output to answer the questions to fill in those blanks, right? So some of these questions, you'll need Stata, for example, to run your regression, but then you have to use the statistics in that regression to answer the actual question, right? So make sure, we're thinking about, like, not everything is going to have a line of code associated with it in these problem sets. A lot of times we're just using Stata output. And in one of those questions, I just gave you the Stata output. I didn't even require you to kind of run that regression. In fact, I took out the variable from the data set that had that. Any other questions before we jump into the material? Okay. So once again, I want to see more of you come to my office with help with these. Like, I want you to kind of learn this, and I'm be there as a resource to help you kind of as we move forward. Yeah.
I just had a question with the exam.
Yeah.
So like, I know you mentioned like you're still deciding like what to put on it, but like for the open-ended part, would you say like it might be helpful to go over our problem sets and then also like all like the in-class quizzes that we've been doing, plus like the slides? I know the slides are missing some of the pictures. So,
all those are good resources.
Okay.
Yeah. Now, I know there's only so much time in a day. So once again, I'll probably go through this a little bit more in depth Tuesday, like on Thursday, next Tuesday's class, but kind of the order in which I do things. The 2 things I mentioned today are the first 2 things I would do. Go through that formula sheet and then start working through those practice exam problems, trying to come up with a solution as to why the correct answer is what it is. And then from there, everyone's going to be a little bit different over is reviewing the in-class quizzes more productive for me, or is reviewing the notes, or is reviewing the old problem sets. But I can kind of give some suggestions on that kind of as we just dive more into review on next 2 classes. Okay. So in order to get to review, we've got to get through the rest of this material. So we kind of talked about some of this already, right? When I'm looking at multiple linear regression, we said I can use multiple dummy variables, right? So one way we can start to do this is maybe I've got indicators. I have 2 dummy variables, right? So if I just include simply both of them, right? So I think about maybe I'm interested that traffic stop data, and I've got kind of a gender and a racial identifier variable, right? But what I'm interested in is, okay, not just are males treated differently, and not just are an individual who's identified as white treated differently, but is that combination treated differently? So if I'm thinking about what I'm looking at there, if I were just to use 2 dummy variables, and maybe I want to see whether or not a ticket was issued at these traffic stops, if I simply include that male dummy, and I include the racial identifier of whether or not the individual is white, right? What will these coefficients tell me? this is the increase in what? If I have this dummy variable, changes in the units would be an increase in the probability someone is issued a ticket from belonging to the one group here. So if they're identified as male, holding constant their race, or at least this one racial identifier we have. What would the interpretation of beta 2 be? The increase in the probability they're issued a ticket if they belong to the one group here are identified racially as white. Now, what that doesn't tell me is the combination of if it's a white male, what is that indicator? Now, I could plug a 1 in to here to both of these, right? And I could come up with different combinations of these two dummy variables, or I could create new dummy variables where I had a 1-0 variable if it was a white male, right? Have another dummy variable if it's a non-white male. Have another dummy variable I created where it's a non-white female. And then the fourth one, which would be what? White female is the only other combination I left out. Now, what's the problem if I run this regression? If I simply kind of think about this as like, gender's not a binary, but let's think about it the way it's coded here, it's a binary. And I have white versus non-white. As soon as I know one of these variables, what do I know about the other three? If I'm a white male, can I belong to any of these other groups? At least the way the data is coded, no. So I would have what issue here? Multicollinearity, but perfect, right? So we said, what would we need to do? We need to come up with a base group and leave one of these out. So I kind of set this up, this is just a different way of thinking about using dummy variables and the issue that we can run into, which is perfect multicollinearity if I'm trying to create every single possible combination of these two dummy variables. So instead of perfect multicollinearity, right? So we kind of have this issue where I need to leave one of those groups out, okay? I often can run into imperfect multicollinearity. Now I mentioned this idea, but these are going to be two variables where just because I know one of them, I automatically don't know the value of the other, but I know that one is a linear function of the other, right? That there is some function that exists where if you tell me variable X, I could tell you what the value of variable Y is, right? Now, it might not always be 1-to-1, right? There might be some kind of a slight discrepancies there, but they're going to be very closely, like they're going to not be perfectly multicollinear, but very closely to that, or close to that. Just use my English language, right? So what's going to happen if I have two variables that are perfect linear functions where they are imperfectly multicollinear, right? One of our estimates, I can get my mouse over here, is going to have huge standard errors, right? So it's not going to mess up my coefficient estimates. So the actual slope coefficients I see won't be influenced if there's imperfect multicollinearity, but what will be impacted is my standard errors. Well, what's a problem if I have really large standard errors? So once again, this is where we're going back, kind of using these statistics. How do I calculate my test statistic? It's going to be my coefficient estimate divided by its standard error. So if my standard errors get blown up for one of these variables, what happens to my test statistic? It's going to be smaller. If I'm thinking about my test statistic, if it's smaller, what's happening to the area to the right of it? It's getting larger. What does this area times 2 represent? Because we're always using a two-tailed test. My p-value. So if my area is getting larger, my p-value is getting larger. Is it more or less likely, and this is kind of the why that sometimes people are leaving out, if my p-value is higher, is it going to be more or less likely it's below alpha? If it's higher, it's less likely it's going to be less than that, right? So because my standard errors are getting blown up or becoming large, it's going to make it less likely for one of those variables I can reject the null when in fact, maybe I should be, right? It's that the standard error is just being influenced by this imperfect multicollinearity, right? So if we think about we can always kind of run through that idea, but here's kind of where it comes from, right? So notice if I have these two variables that are imperfectly collinear, and one of them is a linear function of the other, right? So what could I do here is if I know that x1 is a linear function of x2, I've got like an additional like error term from this regression. I could actually input this in, and what am I really doing? I'm estimating this relationship really with just one of these variables. But when I calculate the standard errors on that X1 variable, it's going to be including all of this error as well, increasing my standard errors. Okay. So what can we do, right? So the example I have here is age and experience. I'll show you some data output that kind of runs us through this, right? So here we go. So I ran this regression and I've got IQ and experience and I've got IQ and age, okay? And I'm trying to predict, well, I'm guessing wages, right? It looks kind of similar to the second problem set. So I ran these two variables separately, and I think that there's some multi-collinearity, because how can I have more years of experience? Well, if I'm only 24, I'm kind of limited in the number of years of experience I can have, right? So the years of experience is going to be some function of how old the individual is. Okay? Now, I don't know what that function looks like, but I know that there would be some connection between that, right? If I'm 24, I can only at max have, I don't know, if you entered the workforce at 18, 6 years of experience. Whereas if I'm 40, I could have 22, right, et cetera. So I'll notice if I run these separately, okay, p-value is a little bit higher on experience, but these are both pretty statistically significant. Age is statistically significant at what levels? P-value of 0, so all of them, it's less than 0.1, 0.05, and 0.1, 0.05, 0.01. Here, experience would only be statistically significant at, so 0.018 is less than 0.1, so 90% confidence. It's less than 0.05, so 95% confidence, or the 10 and 5% significance levels. Not quite at my 99% confidence because it's not less than 0.01. Okay, so this is kind of our setup, right? Now, so they're both significant at that 5% level though. Now, let's say I include them all in the same regression. So I now have IQ, age, and experience. Okay? So I know that one of these variables, their standard errors are going to be messed up, but I don't know which one, right? So when I look at here, if I had to guess which one of these likely has, because I don't know what the standard errors should be, and they look pretty similar here, 3, 4. Which of these can I probably guess has the inflated standard errors? What did we say that inflated standard error was going to do to our p-value? So higher standard errors did what to our test statistic? So it lowered it. A lower test statistic makes the area to the right, which times 2 is our p-value, much larger. So if I'm guessing, which of these likely has the issue? Right? The one that has really high, well, actually it would be the opposite, right? Because it's going to inflate my p-value, make it much larger. Which of these has a really high p-value? Experience, right? So if I had to guess, it's likely that's the one that's being influenced, right? Because if it's making my p-value larger and the p-value is still 0, probably pretty unlikely. Now, that's not a question I would necessarily ask you because it's not a guarantee, right? It could be that the p-value is supposed to be 0.000001, and here it's 0.00001, right? But if I'm guessing, the one that has a really large p-value is probably the variable here that was impacted.
And for the same reason the p-value increases, the t decreases, could you also use the t as an example and say,
I could look at these and say, well, which of these has a really low test statistic? The test statistic and the p-value are completely connected.
what one should you use? Like, is p-value better to use than an indicator?
They're the exact same thing, right? If I have a higher test statistic, my p-value is automatically going to be lower. So I'm really just like, it's almost like I'm looking at two sides of the same coin, right? So really either one would be evidence here, right? It has a really low test statistic and a really high p-value. You see another hand?
Yeah. So if you ask us with like multiple beta variables, like, well, and you ask us like, what would beta 0 be? Would it be just coefficient at the bottom?
Yeah, what's beta 0 in every regression we look at? That's our constant or the intercept. So in our data output, it always looks like CONS constant, or that's our intercept coefficient.
So like regardless how many data is, beta 0 will always be that. Okay.
Yep. Any other questions here? So I'm guessing, it's probably going to be this experience variable that's being impacted, but I can kind of chase this down, right? So I have some solutions to this, right? So I can do nothing, right? And just accept that one of my variables, I'm going to be making the wrong statistical. That's not a good solution, but right? Maybe it's the limitation of the data. What I can also do is try to find Other variables in the data that would represent a similar thing to the variable I think has an imperfect multilinear relationship with the other variable. Now, once again, that's data limitation. I might not have that exist. Now, what's one thing I can always do to help with any type of statistical significance? So if we go back and look at, here would be what we've got, what do I want here? Sure, I'm getting this accurate. Trying to have this pulled open back to it so I can show you kind of where we're thinking about this. So I've got, where's that? Go. So we're looking at our test statistic here, right? We said if I had like a simple kind of linear regression, what that test statistic is going to look like. I've got my sample coefficient. Now, what is my standard error? It's going to be the sum of the differences between y, my predicted y's or my errors squared. And then there was an n-2 if this was a simple linear regression. We didn't really talk about the calculation of standard error when I started to look at multiple linear regression, but really this actually becomes like n-k minus 1. We're not going to do anything that I won't ask you questions on that. But what we can kind of focus on is what happens, and this is almost true for every statistic we're looking at. R squared, we'll kind of look at some other things today. If I increase my sample size, what should that do to every statistics distribution? Make it more peaked, which means I'm driving down either like the variance, or here, what's the variance of my coefficient? That's, well, it's really what's the standard deviation of my coefficient. It's my standard error. So increasing the sample size will always do what? If this denominator is larger, what's going to happen to my standard errors? They're going to go down. All right. This is just the idea that when I have a larger sample size and I'm thinking about that distribution, the variance kind of in my of my slope coefficients was my standard error. So I'm going to get a much more peaked distribution with a higher sample size. So if the standard error is lower, what happens to my test statistic? So that denominator is smaller. The denominator is smaller, our test statistic will be larger. If my test statistic is larger, what's happening to the area to the right of it? Multiply that by 2, that's my p-value. So my p-value is getting smaller. So is my p-value more or less likely to be less than alpha? So one solution, even though I know one of the variables has wrong standard errors, I can just increase my sample size a bunch to kind of try to find that statistical significance still, right? It's not a perfect solution, but that's one thing we can do. And it kind of gets at this concept of always taking higher sample sizes is going to reduce the variance you see for whatever statistic you're looking at, making your test statistics higher, making your p-value smaller, more likely you can reject. So that comes, you kind of have a reminder of this from that formula sheet, kind of what that standard error is in your test statistic equation. So kind of that would be in my denominator. So I kind of walk through the different steps there. So the only other thing we can do is try to transform these two variables and make them into one, right? So this would be like if I had GDP and population, I know that as a country is larger, just inherently, it's going to have a larger GDP, right? Just by having more people. So it's not a one-to-one, right? There's some countries that have larger populations with smaller GDPs, but just I know that as I have more people in the economy, that effect is that GDP has to automatically be higher, right? And so what I could do is do something like GDP per capita, create a new variable, which is the ratio of those two, right? That would kind of solve my multicollinearity issue. I now just have one variable and it captures or it controls for the same two variables I was interested in controlling for before, but it kind of resolves this issue that one of them will have improper or incorrect statistical significance. Okay, so here we go to Stata, and I've got kind of that week 7 one. I think I put post on it because I changed some things for class. So I've got a different example we can kind of think through this with. Okay, so I'm gonna, oh, this is an old data set. Didn't change this, so I'm going to have to actually go to open up this NFL data or QB salary data. So I have all this. QB salary data, which I had up there on Canvas. So wherever you've put that file, you can kind of go in, open it up. So I had this idea of I've got all these different quarterbacks. I've got the total value of their contract. I've got a bunch of different variables on them. So I said, okay, I know that there's two things that matter. Right? If I don't follow football, it's okay. These are just statistics that matter in like how good someone is, right? How many times that quarterback is throwing the ball, right? The attempts, how many times the pass is completions, right? So if I run these two kind of separate regressions, it looks like, okay, how many completions they have, close to statistically significant, not quite. And then attempts, also pretty close, but not quite either. But I think these things probably matter. So I say, okay, what if I put them into the regression at the same time? Well, inherently, in order for someone to catch a pass, what do I have to do? Throw it, right? So every time I have an attempt, every time I know that there's a completion, I know that there had to be an attempt, right? There had to be a throw. So if I run these two variables in the same regression, whoa, not only was one of them impacted, it looked like both were statistically significant before. Now the p-values are like 0.6. I'm nowhere close to statistically significant. And that's because what issue would I have? We just described, well, if I know you had a completion, you caught the ball, someone caught it, automatically I know that you had to have thrown it. It's a direct linear function of the other variable. So I know these p-values are inflated, which makes it less likely I can reject for either variable in this case. We know one has to be impacted, but both of them, this is a good example, can be.
What would that constant represent for those two variables?
Yeah, so how do I always interpret a constant? It's if all the x variables are equal to 0, right? Because before it's simple, it was just when the single variable is equal to 0, it was kind of the predicted value of y. So it's weird. The interpretation often won't have economic significance for us. But if I had a quarterback that had 0 attempts and 0 completions, the predicted total value of their contract would be what? About $1 million. If I'm looking at this right, moving this decimal 7 places to the right. What quarterbacks would this be? No completions, no attempts. Someone who's sitting on the bench, not playing the games, right? So this tells you that even simply being on an NFL team, pretty good compensation. That's a pretty good job to do nothing. Not that they're not doing anything, but you get the idea, right? So that's how we always interpret our intercepts when all the x variables are equal to 0. Now, obviously, we would want to control for a lot of other factors here, right? But I'm just trying to use this kind of idea to get just that imperfect multicollinearity. So what can we? Well, we can do nothing. We can just choose one of the two. We can go out and get a higher sample size. The only problem is here, the data is what it is. I can't like create NFL games, right? So this is the data. I can't go out and get a higher sample size, right? So the one that we kind of have left to us was transforming those variables, right? So if I transform these variables, right, we'll notice that all I'm doing here is kind of taking the number of completions and dividing it by the number of attempts, right? So this new variable is using both those variables I wanted to use as controls that I knew imperfect multicollinearity existed between, and creating a new variable using both of them. So in essence, I'm still controlling for both of them, but I'm eliminating the imperfect multicollinearity, right? And the reason why, if we want to go back, and I won't waste time kind of writing this out, but if you think about, if I take x2 and I divide it by x1 here, if I were to plug in this for x1, notice like x2 would cancel. So in a way, we're kind of getting rid of this imperfect multicollinearity. That's not the most technical way of thinking about it, but for the sake of what we're doing, that's all we need, it's as far as we need to kind of think about it as. So I'm going to create this new variable, which is a ratio of the two, and then run that same regression just using that new variable I created. Now, instead of p-values of 0.6, right? This completion percentage, which controls for both attempts and completions, is highly statistically significant. In fact, not quite at the 95% level, but very close. Right? So we just went from having p-values of 0.6 all the way down to 0.05 of this variable, this transformed variable that we created. Right? Okay, so any questions on that before we keep moving with imperfect multicollinearity? Okay. So that's kind of our main solution, is transforming the variable. All right, so that's what we just kind of looked at. Oops, here. Now, this might be obvious to some, okay? But if I wanted to predict, and we kind of already alluded to this when we were looking at multiple linear regression, let's go back to that wage output. If I wanted to say, what's the predicted wage or dependent Y variable for someone who has 105 IQ, 10 years of experience, and is 45 years old? How could I use this output to make that prediction? So if I've run this regression, and you did this with simple linear regression. So if I'm trying to predict wage, and I've got, this is my, I forgot what was it? IQ, is it age? No, I'm forgetting. Age and experience. So we're using the variables that have imperfect multilinearity, but we're just using this for a different kind of case here. Well, when I run that regression, what did I find? I found my estimates for every slope coefficient and the intercept. So I'm going to have a value I can plug in for every single one of these. Well, if I'm trying to predict my Y variable based off of those coefficients, if I have someone that's 105 IQ, what was it, 10 years of experience and 45 years old, all I'm doing is plugging in those coefficients and plugging in this hypothetical person's values for those variables. It's a literal linear equation that I'm calculating the value from. So that's the whole, I mean, that's the real strength of what we're doing is we can now come up with predictions for any combination of these three variables. Any combination of IQ, age, and experience, I can tell you the person's predicted wage. Okay? So if I'm going back to my output, I've got my three slope coefficients for each variable. I've got that intercept, right? And I've got the three hypothetical values. It's just a matter of kind of plugging those values in, right? So how do we do this in Stata, right? I could do that by hand, right? Just plugging those in and entering it into my calculator. Well, let's look and see how we would do this in Stata, right? So I'm going to skip through this kind of residual stuff here for a second. I might come back if we have time. So once again, there's all these free data sets that live in Stata. We're just going to use one of them right now. So I'm going to kind of open it up. It's a smoking data set. So we'll kind of clear out the old data, open up this new one. It's got a bunch of variables. So I have like the number of cigarettes I think someone buys, their education level, what the price was in that state, racial kind of identifier, dummy variable, age, and what their income was. Okay. So I'd have to look. I kind of think that income was just in dollars. So yeah, it must have been because I'm using 45,000 here. But if I wanted to use Stata to come up with this prediction, what I would do is I'd run this regression. I can then see the coefficient associated with every variable. Now, doing this by hand, you can kind of see as I start to add in more variables, it's just going to take a longer and longer time to enter into my calculator, right? I could tell you, someone with 13 years of education, the average cigarette price is $5 a pack. They're white, they're 35, they have an average income, or their income was 52,139. Well, I could still use the same process. I've got all my coefficients, all my hypothetical values, but that's going to take a while, right? So what I can do, and if I was asking this in an exam, probably not going to give you that many variables, but it might give you 2 or 3, like in the first example. But if we're wanting to do this in Stata, after I run my regression, and apparently I shouldn't even waste time on this because I'd say about, 70 to 80% of you apparently already know this, right? Wink, wink, right? After I run a regression, how can I save the coefficient estimate from that regression? If I use _b, and then in these brackets, the constant has an underscore in front of it, but then it's just, well, what variable coefficient do I want? So if I want to make a prediction, I should be taking the intercept coefficient that we had kind of written down, plus the coefficient on my first variable, education, times the hypothetical value of what that variable would be. And then I want to add to that the coefficient on my second variable, cigarette price, times the hypothetical value of that pack of cigarettes, and then so on and so forth. So this kind of saves me a lot of time where I don't have to make these calculations by hand. I can kind of do this all in Stata here with one line of code. Okay? And then if I want to change the values, the coefficients will all stay the same. So maybe I run this display command. It does the math for me, basically makes Stata my calculator. does the math behind the scenes, but it's grabbing these coefficients, taking these hypothetical values and telling me this person's predicted, what, cigarette used to be 14, and I think this was like weekly or something like that, right? Now, what if I said, oh, wait, I want to make a prediction instead for somebody who has 16 years of education. The average price of a pack of cigarette in that state is $4, and their average their income was 60,000. Well, I can just change those hypothetical values, run that display command again, and it'll tell me their predicted number of cigarettes they're using. Okay? So a lot of you already knew this, right? Yeah. Okay. So this is how you would kind of save the. You don't realize why I'm saying that. It's because a lot of people are using this in their problem set, even though I haven't went through it. So I know that they probably are not fully understanding what that code is doing. Okay. So now hopefully we have a slightly better, all of us should kind of know now, right? When I run a regression, I can use those coefficients using this underscore B and then putting whatever variable I want that coefficient for in those brackets. Okay. All right. Any questions on that idea? Once again, if we're doing this by hand, I won't give you 6 or 7 variables on the exam, but you should be able to do this with 2, 3 variables. Maybe if I had a dummy variable too, maybe I'd give you 4. That is as typical. Now, one thing you always don't want to forget though, when you're making your predictions for that Y variable, what is added into every prediction? The intercept or that constant. So that's an easy mistake people can forget to they leave that out. Okay. All right. So another command that we can use, right, is I can actually come up with a predicted value for every single observation in my data set. So instead of like going through, if I had a couple thousand observations, I can't make up a prediction for every single one using this display, like every line of code. If I run a regression, after that regression, if I use this predict command, right, I need to call this variable something new. So this I'm going to call it's the predicted cigarette use. When I look at the actual data, my Y variable was their actual, I think this was maybe packs per week of cigarette use. Right? So I want to come up with my predicted Y. Okay? So what I'm going to do is just run this predict command. Right? This is going to create a new variable, which goes through, takes those coefficients, and for this first person, it doesn't have hypothetical values. It can use their actual values for education, cigarette price, age, etc., income, whatever, whatever variables we've included in that regression. So notice the actual cigarette use is very different from the predicted values, right? Because when we come up with predicted values, that's kind of on average what that person's cigarette use would be. We always know that we're going to have an error term, right? When we're making our predictions, we don't include the error, but we know that an error exists for every single observation. Right? Just because I'm, have 16 years of education, I'm 46, I have $20,000, doesn't mean every single person with those characteristics smokes 0 cigarettes, right? There's going to be some individual component that I can't measure, right? Because of omitted variables or like my data limitations. So what should be true is when, I think I might have looked at this with you guys with simple linear regression, but I can do it with multiple linear regression as well. So this is my predicted Y, right? If I also use this error predict command, and I'm going to create a new variable called error term, and then comma residual. So when I do this, it's not going to come up with the predicted Y. What it'll do is it'll come up with the predicted Y and look at the difference between that and the actual Y values, or my error term, my residual. Okay. So what should be true if I do this, right? First of all, if I'm creating this second error term, right, it's another variable. This should have taken the difference between my actual Y value and my predicted. So what's my actual Y value? Whatever's in that cigarette variable. What is my predicted? Hopefully, if I told you correctly, what that predict command is coming up with. So if I create this new variable, it should have the exact same value as what this residuals command is telling it to do. So I'm going to go ahead and run that. Sure enough, I kind of look here. The error term using that residual command was the same as if I actually calculated the actual minus the predicted Y values. Now, I don't have to like do both of these. I can always just rely on this one. And I know now that I'll do. Now, what should be true about those errors? we said from a simple linear regression, I've got this scatter plot of data. We could visualize this with simple linear regression. When I drew a line through that scatter plot, on average, my errors from a line trying to best fit that data should be what? 0. Right? My line's going to be under some of them, but above some of them. And on average, it should be giving me these errors of 0. Now, for any one observation, I could have a positive or a negative value. Some will be small, some will be large. So the same thing applies to multiple linear regression, but like I can't visualize that in a 2-dimensional graph because I've got 6 variables. So I would actually need like a 6-dimensional I can't really visualize this, right? But the same principle would apply. So when I summarize that error term, hopefully its mean should be, well, why is that basically 0? What does e to the -9 mean? Move the decimal 9 places to the left, right? So we're never going to get exactly 0 because we're working with a sample, but it's going to be very, very close.
If you have the Y values for a data set, why would you need to predict them and then find the difference?
Because whoever's in my data set, that's not every single person out there, right? I've only got what, 800 observations in this data set. So I might want to come up with predictions for everybody else, right? So really the value in running these regressions is I can come up with a prediction for anyone, right? I'm just kind of showing you come up with the predicted values for this data set, and hopefully we should see that average error we're making is 0, right? But yeah, in practice, what do we want to do with these actual coefficients? We want to come up with, like, if I'm a company, right? In fact, I know someone that does this. I mean, some of you, this might not interest at all, but it's also a way to make money. So if you can go out and web scrape some of the betting lines on any sport, you can figure out, and then look at the actual outcomes. You can figure out actual outcomes will be your Y. You can figure out based off these other variables, whether or not these online gambling companies are making mistakes, right? And then given a game that hasn't happened yet, you can use those same variables going into the game to predict whether or not they're more or less likely to make a mistake. 1, 0 would be our dependent variable if they make a mistake or not. And if I can come up with a game that has the highest predicted probability of making a mistake, that's the game I probably want to bet against that. Or think about a company who's, incorrectly, maybe I want to predict different locations within the same company that are more likely to have theft or the number of theft items that they're having. Like I can figure out what any company's probability or what any company's like number of thefts they would have would be.
Well, if you did like the gambling example, how would you determine like which variable that they used or didn't use that ended up being like the wrong outcome?
Well, that one's a harder because they're running their own models. So probably in practice what I have to do,
You have to test.
I have to know exactly what variables they're looking at. But if I can think of something they're not thinking of and factor into my regression, then I can start to come up with reasons why or I can start to figure out why what they're not factoring into the models would predict they're being right or wrong.
Like another variable that would increase the probability of something happening.
Same kind of thing. It doesn't have to be gambling. Could be stores theft. Could be whatever the example is. Yep. Okay. So where are we at on time? All right. I want to save time for us. So we've talked about scaling variables already, so that's not something I really want to focus on today. We're going to come down here and first talk about, so we've kind of discussed this earlier. So if we had time, I'll maybe come back to this a little bit on Thursday. But we've talked about scaling variables, economic significance already, and the concept of simple linear regression. Nothing changes with multiple linear regression. So the real thing I want to kind of focus on is thinking about this difference between adjusted and our actual R squared. And then we'll kind of have this joint hypothesis testing, which I think we'll probably start today. I'll probably finish out kind of the discussion on it next class. I know that we have kind of talked about this already, but I think this is useful almost in reviewing for the exam as well. So let's think about this R squared and our adjusted R squared, okay? So our R squared, we said, was the proportion of variation our model can explain. So same thing with simple linear regression, has the same interpretation for our multiple linear regression, right? So explain sum of squares was like the variation our model explains. When we look at stata, instead of ESS, I think it looks like it's model sum of squares, so MSS. Those are really just two interchangeable terms. And then the total sum of squares would be the total variation that existed, right? So we would like our R squared to be high. all the variables we include in our regression, hopefully we can explain almost all of the variation in that dependent variable or that y variable. Now, another way of writing this would be, if this is the proportion our model explains, 1 minus the proportion our model doesn't explain would be the same thing. So our residual sum of squares is what our model can't explain. So 1 minus the proportion we can't explain gives us the proportion we can. That's our R squared. We said the adjusted R squared is going to adjust that proportion that we can't explain by this factor. So we're going to think about what that is going to do as we change these things, right? So I wrote a bar above it. I always kind of like using just subscripts. That's just my kind of thing. So if I think about my adjusted R squared, this was 1 minus the proportion you can't explain. And then we were going to scale it by this factor, n minus 1 over n minus k minus 1. So we talked through this before. There's two things that can influence my adjusted R squared. If I have a higher sample size, let's think about what would happen. It doesn't, so k is going to represent the number of right-hand side or independent variables that we've included. Okay? So it's the number of variables we have on the right, not including the intercept. Just the variables that we include in our regression. So if I have a higher sample size, let's just think about if k was 1, just to kind of have this hypothetical. And I'll use some extremes to prove the point, right? But if I have a sample size of, I don't know, 10, right? So that's my n. What would this factor be? 10 minus 1 over 10 minus 2. So what, 9/8? Right? What if I get a higher sample size? So now k is still 1, but my sample size is 100. Well, now I've got 100 minus 1 over 100 minus 1 minus 1. I've got what, 99 over 98? What is this value getting closer to? 1. Right? So as I increase my sample size, what's happening to kind of my scaling factor for my adjusted R squared? As n goes up, right? This scaling factor is getting closer to 1 or going down. So if I'm subtracting a smaller amount, what's going to happen to my adjusted R squared? It's going to get higher. If I subtract a smaller amount, it's getting higher, right? Or if this scaling factor was 1, what would my adjusted R squared be equal to? Squared. Yeah, if this is 1, I'm just left with this. That's my R squared. So the adjusted R squared, when it gets higher, another way of thinking about this, it's approaching whatever our original R squared value would be. Okay? Because we're not really having to over penalize our R squared by much because we have a really large data set, right? That's kind of the intuition, right? But you can walk through the actual, I'd like to use these arrows. I think that's maybe the easiest way to think about it when you're solving these problems. But the idea is that I have larger data sets, right? The data I have should be more reflective of what the actual scenario is, or my R squared, right, doesn't need to be penalized as much. You can think about it that way. Now, what if k is getting larger? Okay? If k gets larger, right, what's going to happen? I guess I've got colors so I can kind of cheat. So I'll write this out here again, just so we can kind of see it on a separate line. If k is getting larger, I'm adding more variables on the right-hand side. So intuitively, if I have more variables, should my predictions be more or less accurate? More. I'm controlling for more factors. So what should happen? Should I penalize my R squared more or less? Less. So my adjusted R squared should be getting closer to the actual R squared. Well, we can reason through, hopefully that's why, right? So if I subtract a larger value in the denominator, what happens to my denominator? It's going to be going down. If my denominator here is smaller, what's happening to my scaling factor or my penalizing factor? Bigger. The denominator is smaller. This fraction is going to be going up. If I'm subtracting a higher value, oh, tracking a higher value, my adjusted R squared is actually doing what? Going down. So this is where your intuition might not lead to the correct answer, because when we include more variables on the right-hand side, yes, we're trying to come up with more accurate predictions, but how did we have to do it? We had to throw more variables at this regression. So the more variables we use, we actually want to penalize the use of them, right? Because if I just throw 1,000 variables, even some that don't really matter, I can always, we said, as I add more variables, what always happens to my R squared? Even if the variable is like not statistically significant, but it explains 0.0001%, it's always going to explain a little bit, right? So adding in more variables will always increase my R squared. So we know that's going to be the case. So we penalize adding in more variables in the adjusted R squared. That was the reason why we're even coming up with a statistic, is because we wanted to kind of make sure that people aren't just throwing, like guessing what variables might matter, right? So higher sample size increases our adjusted R squared. The gap between our R squared and adjusted R squared is getting smaller. If you start adding in more variables, that penalizes the adjusted R squared more, it's going to get lower, or it's going to get further away from the actual R squared. Okay. So we can see this with some actual data. So we have time. We still got 20 minutes here. First of all, before I go back here, are there any questions on this before we keep? Okay. So I'll show you an example here real quick. So we had this cigarette data pulled up, right? So let's say I run this regression where I'm looking at cigarette use, and I've just got, I don't even know. I think this was that you could smoke in restaurants. I think this was a dummy variable. This is a slightly older data set. This isn't as prevalent now. Age and income and education to try to predict cigarette use. So I run this regression. I look here. Okay, what's my R squared? 0.019, and my adjusted R squared is 0.014. Okay. If I include more variables, what should happen to my R squared? It should go up, right? So if I include some variables that might matter, I'm guessing cigarette price probably matters quite a bit, right? And I run this new regression with additional variables, my R squared should be higher, but notice, oh, actually didn't really impact it that much, right? So I can't see that it increased it, but even though I can't see out to the 4th decimal, I know that at some decimal, adding in these variables increased my R squared, right? So we can't see it out to the 4th decimal here because it didn't change how much we could explain by very much. Now, why didn't it explain much? If I look at those two variables that I included in my regression, are they anywhere close to being statistically significant? A p-value of 0.9. Are we anywhere near alphas of 0.1, 0.0? No. So if I add in variables that aren't statistically significant, what's going to happen to my R squared? Is it going to go up by much? No, because they don't have much explanatory power. They're not statistically significant. Now, it still will go up out to some decimal that we can't see, maybe the 6th, 7th. We're not 100% sure. In fact, let's see if I can remember the syntax off the top of my head here. So we'll go. I think this is what I wanted. See if I can remember the. It's not. It's going to be underscore R2 maybe. This is where even I need a code book sometimes. Oh, I can't remember what it is. It's E something. I'll cheat. E. Oh, it should be it. Was I capitalizing it before? Yep. So this is where I forget sometimes too. I can't capitalize that. So let's say here, I run these two again. I won't expect you to know this. Once again, some of you apparently already do. But if I run these two regressions, I can actually display the R squared. So notice it like went from what, 0.09 or 0.01903 to 0.01904. So it did go up, right? I just couldn't see it to the fourth decimal, right? Now, if instead I'm thinking about my adjusted R squared, so I've added in these variables, they didn't really increase the R squared by much. What should happen to my adjusted R squared? Instead, if I increase K,
Goes down.
it should go down, right? So if I look at those results, in my original regression, the adjusted was 0.014. After I add in those variables, what happened to my adjusted R squared? It's a little bit lower, 0.011 now instead, right? So higher number of variables on the right-hand side lowers that adjusted R squared, okay? And this was a good example because it didn't change the R squared by much. So what was happening to that gap in between the R squared and the adjusted? It was getting larger, right? Now I could also do a similar thing. You would never want to actually do this in practice, like just to kind of point this out. But let's say I run this regression, right? And I've got my output. I've got the R squared was 0.019 and the adjusted was 0.0117. It's the same regression we just ran. If I make the sample size smaller, right, what should happen? Well, if my samples, everything we went through here, I could do a smaller sample size effect as well. If the sample size is smaller, what happens to my scaling factor? It'd be going up. If my scaling factor is going up, I'm subtracting a larger value. So my adjusted R squared should be getting smaller, right? Smaller sample sizes, less reliable results. My adjusted R squared will kind of penalize that I'm finding these results from a small sample. So if I just create a random number and then I run the regression for only these 100 observations as opposed to the 800, what should be true, my adjusted R squared should be lower than 0.011. So I'll go ahead and run that. In fact, because my sample size is so small here, notice what can happen to my adjusted R squared. We get negative values here, which doesn't really make sense, but that's because we have a pretty poor regression here, right? The R squared of 0.05 or 0.01, that's a really low proportion explained, right? So technically our adjusted R squared can show up as negative if we have regressions that really we're not doing a very good job capturing a lot of the variation in that dependent variable. Right? It's just a byproduct of how we calculate them. Okay. All right, but here what I'm really wanting you to focus on is the directional changes. Those are the types of questions I'll ask you, right? So where are we at here? 10 minutes. Let's see. So I will save joint hypothesis testing for next class. That'll be the last thing. So I thought we'd get through everything today. A little bit more new material on Thursday, but it'll also kind of lead us right into jumping into reviewing. It's not a whole lot. It's nothing too crazy. It kind of coincides with what we just finished on adjusted R squareds. And let me see here. But hold off until you try to access this for just a second, because I've got an explanation. Told you that I wasn't really liking the number of people I'm seeing here in class based off the number of people I'm seeing responded to in-class quizzes. So I might come up with a way to solve that issue. Don't like to have to do this, but our hands are tied here by actions. So we'll kind of go through this. So if you try to open up this quiz, can you do it? Anyone get it to open up?
Is the access code required to start?
Yeah, all right. So I'm going to start putting a number on these quizzes so that unless you're in class, I mean, I guess if you can guess the random number that I'm coming up with, then good on you. But today's number is going to be 13.13 or 13.13. That should get you into the quiz.
0.13.
13.13. So that should then allow you to see these, okay? Now I added this in as a fail-safe. I wasn't sure if this was gonna work. So if you want to just put this in right away, same number as what I just gave you as the last question. I thought this would work. I'm using the new quizzes in Canvas. I've never actually used that in class as kind of the requirement. So I was wary of it. So I wanted to make sure I had a backup plan to kind of identify that you had the number, okay? So this won't really be what I'm doing kind of moving forward. We'll kind of have one of these access codes where I give you the random number at the beginning to access the quiz, okay? So here maybe is some questions where we start to think about we could do like some review. Right, so I've got this quiz pulled open. If I think I've got imperfect multicollinearity between the cost per pack and tax per pack. So why would I have some multicollinearity going on here that's imperfect? That's an Econ 101 stuff that we're gonna go through.
The cost per pack is directly influenced by the tax per.
If I tax something, what does that do to the price the consumer pays? Increases it, right? So I automatically know that when I have higher taxes, the price per pack has to be higher. They're a linear function of each other. So what's gonna happen with my estimates? One of these variables at least is gonna have what? We can say that, but I would start with the initial thing. The initial thing is it's gonna cause the standard error of one of the variables to be too high. If one of these standard errors is too high, what is that gonna lead to? A test statistic that is too low, then a p-value that would be too high, and I'm gonna be less like, if I had to guess once again, which of these variables is being impacted by this imperfect multicollinearity in terms of its statistical significance? Probably the one that has a p-value of 0.4 and not 0. So in one example I showed you with Stata, we had both variables being impacted. Here, it's probably more that one of them is being impacted more than another. Okay? So if I'm looking at this, which of the following is going to be true? Well, we can kind of say the standard error of cost and tax will be larger. The standard error of all variables included will be larger. The standard error of only tax per pack is going to be larger. Or the standard error. Well, hopefully, we know the standard errors can't be accurate, right? It's not every variable in this regression. It's only the two variables that we are concerned about the imperfect multicollinearity between. However, if I'm thinking about the standard errors, it could be that both of them are large, right? Or it could be that only one of them is going to be impacted. So if I'm thinking about kind of which of the following will be true here, excuse me. I don't know that both will be larger. I know that at least one of them will be, right? So I probably wouldn't ask you a kind of as tricky of a question as this on the exam. I would probably leave this one more likely to be open-ended of explain what's going to happen to the standard errors of the variables in the regression. Year won't be impacted at all. It didn't have any imperfect multicollinearity with cost or taxes, right? It's not necessarily that both of them will be impacted, right? It's that at the very least, we know one of the variables will be. So that's all we can say is that at the very least, only one of these, right, which the following must be true, only one of them. Both of them could be, but they don't have to, right? But we know one of them will be, right? So kind of the standard errors of only tax per pack will be larger there, would be our answer. Any questions on that idea? Once again, I would probably make something a little bit easier than this just because I probably wouldn't give you both of these possible answers. Or I would phrase it differently as though I know both of them will have to be increased or something along those lines, okay? So we didn't quite get to this one today. So we can kind of ignore question 2 and I'll kind of only grade you off the other 2. We also didn't get to question 3, but we can kind of already think about question 3 relative to what we've talked about before. And I'll kind of lead us into kind of next class, thinking about a kind of consistent theme across a lot of the different topics we've been talking about. Okay, so on question 3, let's say, so joint significance, when we were looking at that or R squared and the adjusted R squared, we said as I add in more variables, I might want to know, okay, when I went from a model that only had 4 variables, if I've included 3 other variables as well, adding them in at the same time, I don't want to test the individual significance of each variable. I want to know if adding all of them in at the same time had simultaneous significance, if we want to think about it that way. So next class, we'll talk about how we come up with one statistic, the F statistic, to measure this. But for now, we'll think about this F statistic as just a measure of how well, right, adding in these 3 variables at the same time was able to increase our R squared. Right? How, were they jointly significant, simultaneously significant? So if I'm thinking about, instead of having a sample of size, well, I've got 100 here. Let's say instead we had 3,000, right? So I'm going to have a really large sample size, okay? So like most things, right? And I'll kind of even cheat a little bit and show you the formula that we'll start looking at. Oh, maybe. There we go. So we'll go down here. And I just want to kind of make the point today so we can start to see these consistent themes. So I'm scrolling down, I've got my F statistic down here. Okay. So kind of write this down real quick so we can switch on and off. But basically, this statistic is going to be a way of capturing whether or not we had multiple variables having simultaneous significance. So when we walked through all these other things, we said having a larger sample size generally does what? It did what to the distribution of the statistic we were looking at?
Decreases.
So if we have higher sample sizes, it decreases like our standard errors for our coefficient. Really, we can think of like our denominator down here. This is like the standard deviation of our F statistic. It's not really exactly what we would call it, but that's a good way of thinking about it to kind of connect the dots between what we. So if we have a larger sample size, that standard deviation is going to get smaller. What did that do to our test statistic? Smaller standard deviation or a smaller denominator made the test statistic larger, which made our p-value smaller, making it more likely we could reject the null. So if I think about this F statistic, I'm just going to write it out, and we don't have to be concerned with the numerator because there's no n there. There's no sample size. As I increase my sample size, what's happening to this fraction? It's going. I said you could think of this like it's the standard error of this new F statistic, but it's really just a test statistic coming from a different distribution. Just like our coefficient, it's just now instead of the t distribution, it comes from the F distribution. So smaller denominator does what to our F statistic now? Increases it. Now F statistics are only one-sided, but it still has the same principle. If I'm looking at a larger F statistic, what's happening to the area to the right? It's getting smaller. The area to the right now, I don't have to multiply it by 2. We'll talk about this a little bit more on Thursday's class. But the F statistic, if I add in more variables, we said what always has to happen to R squared? I even looked at it out to the 5th decimal. It always has to go up. So we know we can only see one directional changes. With a coefficient, I can find a negative or a positive value. Here, I know the R squared is going to go up. But that area to the right of my test statistic, it's now not a t statistic, it's an F statistic just coming from a different distribution. That's going to represent my p-value. So my p-value gets smaller. We still determine statistical significance with the same thing. If my p-value is smaller, is it more or less likely I can reject? No, it's smaller, right? More likely, right? It's more likely it's going to be less than alpha. So it's the exact same kind of step-by-step thing that we had for the slope coefficient, right? When we took higher sample sizes, we get the same thing for our joint significance, right? So we're looking at individual one variable statistical significance. The sample size has the exact same effect as if we're looking at the joint significance of multiple variables if we took a large sample size. Any questions on this?
Can I ask what the F statistics measuring?
Yeah, so we look here, right? And we'll talk more about this on Thursday. Anything else? So if you're submitting the quiz, as long as you got into it, I know you had the right number, just put in that correct number that we had at the end. Kind of this one, we're looking for what's going to happen. The F statistic was larger. Our coefficient estimate, that doesn't get impacted. The gap in between will increase and we're more likely to reject. So this would be the one that's not true. Our coefficient estimates won't be necessarily impacted. So make sure you're getting the response into here. I think I had it set to be 335. Really, as long as you get that correct number in, even if it's a little bit late here by a minute, I'll kind of go in and I, based off of this, can kind of give you full credit for being today. Okay. And we'll review the question that we didn't get to in class tomorrow, just to kind of answer your question. We're going to go through that more on Thursday, but the F statistic is basically a measure of when we add in these additional variables, how much more of the variation can we explain? We know R squared went up, but how much did it go up by? And was that a statistically significant increase? So we'll kind of start with that on Thursday, talk about joint significance, and then we'll move on to be looking at that practice exam, doing a lot more review. So everyone clear, as long as you got that kind of number for that last question, I can kind of go back through and update the grades. So don't panic the next 5 minutes when you see the grades, or if it shows up as late, I'll kind of go back through and make sure I get them updated. Okay. All right, we'll see you guys on Thursday.
You made a second.